Welcome back to The Explainer. Today we're diving headfirst into a massive, honestly thrilling structural paradigm shift in computing architecture. We are unpacking the evolution from the centralized, traditional cloud to the ultra-fast, dynamic frontier of the edge. As our modern apps demand unprecedented levels of real-time processing and immediate responsiveness, understanding exactly how and why we are pushing compute power out to the absolute perimeter of our networks, well, it's absolutely crucial. It's basically the foundational concept for the future of our digital infrastructure.
Okay, let's dive right into this. Here is our learning roadmap for today. First, cloud computing and its limits. Second, the latency and RTT problem. Third, waves of edge innovation. And finally, exploring IoT edge platforms.
Section 1. Cloud computing and its limits. The distant giant.
For decades, the centralized cloud has been the absolute powerhouse of our digital infrastructure, right? Consolidating all that compute and storage into massive hyperscale data centers gave us incredible economies of scale and allowed for super rapid software deployment. But this model faces severe, literally unbreakable physical limits when it comes to supporting modern mission-critical applications. Think about it. When an edge device or a sensor processes information, that data has to travel through thousands of miles of cables just to reach a centralized data center. And even using state-of-the-art fiber optic networks, data transmission is strictly bound by the laws of physics. Light in a vacuum travels at roughly 300,000 kilometers per second, sure, but inside a fiber optic cable, it actually travels at about 2/3 of that speed. When you add in all the processing delays at various network switches and routers along the path, this immense physical distance creates a massive propagation delay. That delay is fundamentally at odds with modern applications. I'm talking about things like autonomous driving, automated grid management, or high-frequency trading. In those scenarios, reacting just a few milliseconds too late renders the compute entirely useless or, honestly, outright dangerous.
Section 2. The latency and RTT problem. The villains of speed.
Let's talk about latency. We define latency as the delay before a transfer of data begins following an instruction. You all probably know this as that annoying buffering on a video, or that weird, frustrating delay when your smart home doesn't respond right away. Now, in legacy systems, latency was really just a minor inconvenience. But let's scale that up to the demands of modern industrial tech. Imagine an automated manufacturing arm operating at ridiculously high speeds on a factory floor. If a sensor on that arm detects an anomaly or an obstruction, it needs to stop instantly. If that instruction has to be sent to a cloud server hundreds of miles away to be processed before the stop command actually comes back, you might be looking at a 50 to 100 millisecond latency. In that tiny fraction of a second, the robotic arm will have continued to travel several inches. That could cause catastrophic failure to the machinery, or worse, endanger human workers. It's the exact same story with an autonomous vehicle traveling at highway speeds. It desperately requires single-digit millisecond latency to apply its brakes safely in response to a sudden obstacle. Relying on a distant, centralized cloud to process that visual data and return a braking command simply introduces a critical, completely unacceptable delay.
Closely related to latency is round-trip time, or RTT. Simply put, this is the time required for a signal to travel to its destination and back again. But here's the catch. In modern networking, a single action rarely requires just one round trip. Think about the compounding nature of application architecture today. Just setting up a secure connection requires multiple TCP and TLS handshakes. An application might need to make several sequential API queries, followed by a database lookup, all before it can actually return a result. So, if the physical distance dictates a base RTT of, say, 40 milliseconds, a process that requires just 5 sequential back-and-forth round trips suddenly balloons to 200 milliseconds. In the lightning-fast world of real-time AI inference, machine vision, or high-frequency trading, this compounding RTT is a massive architectural bottleneck. This sort of cross-country road trip for data packets literally becomes the limiting factor in how fast our technology can operate, regardless of how much incredible processing power is sitting in that distant data center.
Comparing these computing models highlights the core architectural shift required to solve all of this. The traditional cloud is centralized and physically distant, which means it inherently suffers from higher latency and those compounding RTT issues. Edge computing, however, is radically decentralized. It operates on the brilliant principle of bringing the computing power out of the massive data centers and dropping it right at the local perimeter of the network, exactly where the data is being generated. By processing data locally on the device itself or on a nearby localized gateway, edge computing physically eliminates the distance. Boom, problem solved.
This is what enables that ultra-low, single-digit millisecond latency modern tech desperately needs. It is a very intentional architectural trade-off. We are moving away from the infinite centralized compute power of the cloud in exchange for the distributed, localized compute of the edge that guarantees immediate response times.
Section 3. Waves of Edge Innovation. Moving to the edge.
So how exactly do we bridge this gap and transition from the cloud to the edge? Well, the shift from a centralized model to a highly localized one certainly didn't happen overnight. We can actually map out this evolution through 3 distinct historical steps, which represent the waves of innovation required to push computing away from the center. Step 1 was the era of centralized cloud processing. This was the rapid expansion of those massive hyperscale data centers, where enterprises essentially lifted and shifted everything into a consolidated environment for efficiency. Step 2 involved decentralizing the architecture to fight the very latency issues we just discussed. This is where we saw the rise of content delivery networks, caching static assets closer to users, and the whole emergence of fog computing. Here, network operators began utilizing micro data centers and regional telecom nodes to process data just 1 or 2 hops away from the end user rather than sending it all the way back to a hyperscaler. And finally, we arrive at step 3, localized edge computing. This is true device-level and local network computing. We are talking about IoT gateways installed directly on factory floors, embedded AI chips executing machine learning models right there on security cameras, and processing nodes built seamlessly into smart vehicles. The compute environment is entirely localized, meaning the data doesn't even need to leave the immediate physical vicinity to be analyzed and acted upon.
Section 4. Exploring IoT Edge Platforms Powering the Frontier.
Now, what's really interesting is how we ground this theory in reality. Because this shift to the edge fundamentally changes how we manage infrastructure. You're no longer managing a handful of massive servers in a secure, climate-controlled facility. No, you're attempting to manage millions of disparate, decentralized edge nodes deployed out in vehicles, on factory equipment, and in remote field locations. It's a logistical nightmare. But major tech leaders have built dedicated platforms specifically to solve this. Microsoft's Azure IoT Hub, for instance, is designed around the core functionality of securely connecting and managing these massive fleets of decentralized devices. It handles the immense challenge of provisioning devices at scale, managing digital twins to remotely monitor the state of physical hardware, and ensuring secure bidirectional communication across local networks that might be, frankly, a bit unstable. Similarly, Amazon's AWS IoT Suite focuses heavily on pushing the actual processing logic right down to the edge. Through tools like AWS IoT Greengrass, organizations can deploy machine learning inference models and Lambda functions directly onto the local edge hardware. This allows those edge devices to process data locally, react instantly with ultra-low latency, and then later sync only the essential, summarized insights back to the central cloud when a network connection is convenient.
I'm going to challenge you to take your knowledge a bit further today. Go out and explore some of these recent edge computing platforms on your own to see this evolution in action. Investigate emerging open-source platforms beyond just Azure and AWS to see how the industry is solving latency right now. Look into lightweight Kubernetes deployments designed specifically for the edge, like K3s, and explore how major telecommunications companies are currently integrating 5G networks with multi-access edge computing to push this frontier even further. It is a really fascinating space.
So as we wrap up, I want to leave you with this thought. As processing becomes increasingly decentralized to defeat latency and RTT, we really have to ask, will the traditional cloud eventually become obsolete? What actually happens to the distant giant when the frontier becomes the new center? It's a massive question about the future of our digital infrastructure. Keep learning, keep questioning, and I'll see you in the next explainer.